Calculus. In this video we're going to be talking about extrema and average rates of change. Our I can statements for this lesson are: I can describe the change in a function as increasing, decreasing, or constant. I can describe the three critical points of a function: maxima, minima, and inflection points. I can approximate the extrema of a function using a graph and table. I can use a calculator to approximate the extrema of a function, and I can find the average rate of change between 2 points on a graph. Our outline for this video, we'll be talking about the difference between increasing and decreasing in a function. We'll take a look at the two types of critical points, extrema and inflection points. Then we'll take a look at how to find extrema using your Inspire calculator, and how to use extrema for an optimization problem. In this case, it will be the volume of a cylinder. We'll take a look at the average rate of change of a function, and then use that average rate of change to find the average speed of an object. So let's talk first about increasing and decreasing. The graphs of functions, really generally curves, do have a slope. Now we're used to talking about slopes in straight lines, but we can talk about the slopes of curves, and that's actually a big part of calculus that's coming up. When a graph generally moves up and right, we refer to it as increasing. Generally it has a positive slope. When a function moves down and to the right, we call that decreasing. That means that generally it has a negative slope. And if the function is horizontal, we call that a constant. It has a zero slope. So let's take a look at a function on our graph. We're going to see this function several times today in this video, and we want to talk about where is this graph increasing and where is it decreasing. So we see that it starts out generally going up and to the right at the first part of the graph. So it's increasing from negative infinity to negative 1. Now that negative infinity to negative 1 is an interval. It's not a point. We do not say that it's increasing at negative 1. There's a calculus reason for that. After it's increasing, we see that it's decreasing from negative 1 to 1. Generally the graph is going down, has a negative slope. And then again it's increasing from 1 on to positive infinity. So we have general regions of increasing and decreasing shown with the red arrows. Now when we take a look at a table, we can see where it's increasing and decreasing by looking at the y values. Here I have a table from x equals negative 3 on up to x equals 3. It's for the same function that we just looked at, and we see the f of x value for each of those. We see again that our numbers are increasing from the left side of the table, negative 3, all the way up to negative 1. It's increasing. From negative 1 to 1, that y value is decreasing, so it's going back down. And then again, the table shows that it's increasing again from 1 on up. So we can take a look at a graph to figure out where regions are increasing and decreasing. We can take a look at a table to figure out where it's increasing and decreasing. Now we have two types of critical points. We have extrema. Now those are separated into two types, maxima and minima. Now when I'm using the ma, that's our plural. A point can be a maximum point, but when we talk about several of them, that's called a maxima. That's a high point in our graph. That's a top of a hill. The minimum point, or the minima, when it's multiple points, are the low points. They look like a valley in our graph. We have both relative and absolute maxima and minima. And then after all that discussion about extrema, we also have critical points that are called inflection points. Now these are a big deal in calculus. All of these critical points are a big deal: maximums, minimums, and then inflection points. Now the inflection points are where the concavity changes. Now that may be a little bit weird term to you, but concavity is an idea about the shape of a graph. We'll talk a little bit about it. So let's take a look at another graph, and we want to decide where are the critical points, where are the extrema of this graph. And we see that there is a relative maximum at negative 1.52, and that relative maximum value is 2.07. Now when we ask where is a critical point at, we're always giving the x value. The x value is a location. And then if we ask what is the maximum value there, we want to give the y value. So when we ask where is it at, we give the x value. When we want the actual value of the maximum or minimum, that's the y value of that coordinate. Now here is a relative minimum. Okay, it's at negative 0.306 and its value is negative 0.311. Again, that's the x value and the y value. And then the graph continues on up and it has an absolute maximum again at 1.08 and 3.04. I'm sorry, I kind of blew over that word absolute here. This is an absolute maximum because it is higher than any other point on our graph. So it's not just a relative maximum. It's not just higher than the points around it. It's higher than every other point. So instead of calling it a relative maximum, it's an absolute maximum. Now this graph does not have any absolute minimums. Those two end behaviors go down forever. So it has an absolute maximum, that very top point, but it has no absolute minimum because it keeps on going down forever. Now let's talk about the inflection points. The inflection points are where our concavity changes, and that means that it moves from concave up or concave down. A function has concavity. I like to explain it like, think about a cup or a bowl turned upside down or right side up. If it can hold water, that's concave up. If it can't hold water, that's concave down. So when we look at our graph again, this first region, this hill that we have, that's all concave down because it's like a bowl tipped upside down. It then changes to a region of concave up. That valley in the middle is concave up, and then it switches back to a concave down. So this graph actually has two inflection points, 2 points where it changes concavity. So those two inflection points are right about there. Now when we get into calculus, we have a great method for actually finding the inflection points. I'm not going to ask you to locate any inflection points, but I do want you to have heard the term. I do want you to be somewhat familiar with the idea of concavity, and those points where it changes concavity are our inflection points. Now, in order to find extrema using our calculator, it's actually a pretty easy process. We have to have a graph up like this, and then we go into our menu. So after we hit the menu button, this pops up, and the way that we find our maximum or our minimum is we go to this Analyze Graph option. Inside that menu, we can choose to find a minimum or a maximum. We can't do both. It will only do a minimum or it will only do a maximum. Now we can do this several times. So if we've got several minimums to find, we can find one minimum, find another minimum, find another minimum. Or if we've got several maximums, we can find one, move on, find the next. So choose whatever we're looking for, whether it's a minimum or a maximum. And then you'll get this question, where do you want the lower bound? And you use your pad to move this vertical line back and forth. You want to be to the left of the maximum that you're trying to identify. So I've placed my vertical line to the left of that first maximum value. You can see up in the corner of the screen, it reminds you that you're finding a maximum. Once you click on that, then you have to drag over to the right side. And you can see your maximum start to show up. Just as you get past it, that maximum will start to be labeled. They label it with a maximum, and they give you the x value and the y value. You click on that, and that point will now stay. You can drag it around, but notice the nice point that they put there. So the calculator does a great job of this. Again, we have a really nifty way of doing it in calculus, but the calculators do a great job of finding our maximums and minimums. Now this is an estimate. These decimals do go on farther, so pay attention to how many decimals you need to go to for your answer. Now, let's talk about using Extrema for optimization. Again, this is a great problem in calculus. We've got some really cool ways of doing this, but what we're going to do is actually end up using our calculator to find this maximum value. So let's take a look at the problem. It says a glass candle holder is a right cylinder with a total surface area of 10 pi square inches. Now, if you stop and think about a glass candle holder, it's going to have a bottom but no top. So that is an open-topped right cylinder. It says find the radius and height that will maximize volume. Now they're giving us the total surface area, but we could make this a very short, wide candle holder, or we could make it a very skinny, very tall candle holder that uses that same surface area. We're trying to find the right combination of radius and height that's going to maximize the volume, that's going to have the most candle in there. So our surface area is 10 pi, and I've gone ahead and I've put up here the expression, how do we find the surface area for an open-topped right cylinder? And we have pi r squared plus 2 pi r h. So that's my surface area for this open-topped cylinder, and I set it equal to 10 pi. Now this is what we refer to as a constraint equation. What it does is it relates absolutely our radius and our height. And this is one of the more difficult parts of this problem, coming up with our constraint equation. Just always look for the number that they're giving you. That's going to be involved in your constraint equation. So I've got my constraint equation. What I'm trying to do is solve this for a variable. Now, the reason I chose to solve for h is it only occurred once, and it doesn't really make sense to try to solve this for r, because not only does it occur twice, but in one spot it's r squared. So it's a lot easier to solve this for the variable h. And now I need an equation to actually maximize. Now whatever we're trying to maximize or minimize, we need to write an equation for that. So since we're trying to maximize volume, the volume of any right cylinder is pi r squared h. That's our base area times the height. We're going to go ahead and substitute in what we found for h. So we replace that h with our 10 minus r squared over 2r. So finally, this is the equation that's going to get plugged into our calculator, and we're going to make our calculator do the heavy lifting. I know, you're probably thinking, I did enough work. Now I'm going to let my calculator do it? Yeah, compared to what the calculator's about to do, what we've done so far is pretty simple. So we go to our calculator and we type in, again we have to use x instead of r, but we type in our equation. So I've got pi x squared times 10 minus x squared over 2x. And I'm not really worried about simplifying that. You know, I could distribute the x squareds in, I could distribute the pi. It doesn't make my life any easier if I do that. It doesn't make the work any easier on the calculator. So just leave it. You know, we got other things to worry about than simplifying that. Looking at the graph, we've got this great maximum right there, but where the heck is it? So I go through my maximizing procedure on my calculator, and I find that point is 1.83 comma 19.1. Now, you need to remember, don't just jump to any conclusions here. You've got to remember that your x is actually equal to your radius for your jar, the radius for your candle holder. And what your y is giving you is your volume. So we have looked at where our maximum volume is, but that doesn't answer the question. The question is, find the radius and the height. I'm halfway there. I've got my radius. Now how do I get my height? Well, I plug it back into that h equals. So I plug my 1.83 in for my r in that equation that I made that said h equals 10 minus r squared over 2r. And I find out that my height is 1.82. Now it's kind of a coincidence here, don't read too much into this, that the radius and the height are close to each other. Don't read too much into that though. Don't think that once you find one number, you found the other one. Okay, just think of that as a coincidence right now. Now, let's talk about average rate of change. When we talk about average rate of change, we're really just talking about the slope of a secant line. Now I've gone ahead and drawn in a secant line into this graph. A secant line is a line that goes through a graph in 2 points. Now this line may go and end up going through the graph in another spot. Doesn't matter. As far as I'm concerned, it's got 2 points that it goes through that are interesting to me. And I want to find the slope of that secant line, and that's my average rate of change. That's my average slope for this function. Now specifically what I did is I drew this in for the points -2 to -1. So this is a range, excuse me, this is a domain. This is from x equals -2 to x equals -1. And it's just a slope calculation. If you remember your slope calculations from algebra, slope is equal to y2 minus y1 over x2 minus x1. Now that doesn't change. That slope calculation is never going to change. What changes is how we find it. So instead of y2 and y1, how do I find those? Well, I plug in my x values into my function, and that gives me my y value. So f of -1 minus f of -2 over -1 minus -2. Now I could switch those -1s and -2s as long as I'm consistent. I try to just go my biggest number minus my smallest number, and that keeps me safe, but you can switch them as long as you do it consistently. Now when I do this, f of -1, I plug it into that equation you see on the screenshot, I get -2 minus, and then f of -2 is equal to a +2, and my change on the bottom is 1. So the slope for this red secant line is -4. That's my average rate of change. It's just a slope calculation. Now let's use that to find an average speed. Average speed is a great application of the average rate of change. It says here that the height of an object thrown straight up from a height of 4 feet is given by g of t equals blah blah blah, where t is time in seconds. So whenever I plug in to this function, I'm plugging in a time. Find the average speed. We can think of that's just find the average rate of change from 1.25 to 1.75. So this again is just a slope calculation. To get my y values, I plug those times into the function. My x values are my 2 times that I'm plugging in, 1.75 minus 1.25. So when I actually plug these numbers into my function, my g of t, I get 7.5 minus 16.5 on the top. 1.75 minus 1.25, well, that's 0.5. It was a half-second interval of time. A little bit of calculator work, and I find out that my average speed for this time is negative, and that's okay. We'll deal with the negative. That just means that it's falling. It's going down -18 feet per second. All right, so that's it for this lesson. I'll see you in class, and I'll see you online.